Good. Okay, hi everybody.
But just Jonas,
Yes.
Jonas, also we see the Zoom
Yes.
screen
Let's see.
on the right. Yeah. I mean, for example, I see myself. Oh, okay, no, better. Yeah.
Yeah, I think. Yeah, I don't know, but I will leave it maybe
Fine.
at this.
Okay. No,
I think
it's
it's
fine.
fine.
Yeah.
Yeah.
Thank you.
Okay. Thanks. All right. Hi everybody. I'm Jonas Berx. I'm a postdoctoral fellow at the Niels Bohr Institute in Denmark, and I will talk a bit about my work on the universal thermodynamic bounds on Fano factors. And specifically, I look at discriminatory networks of biochemical processes. So what do I mean with biochemical discrimination? So on a microscopic level, many biological processes are able to differentiate between something that is right and something that is wrong. And what do I mean with that? So let me illustrate this by an example. So let's take mRNA transcription, for example. So an RNA polymerase unwinds a DNA strand and needs to make mRNA from that. So it needs to match base pairs in the correct order such that the mRNA has the correct base pair for every base that it encounters in the template strand of the DNA. But of course, on this level of description, fluctuations play a huge role, and errors can be incorporated at random places. So if we look at the experimental data, we see actually that the error in these biological processes is very low. Of course, we don't want our DNA to be full of mutations, and we want our proteins to fold correctly. So it makes sense that the error needs to be as low as possible. But if one were to assume that this all happens in thermodynamic equilibrium, then we would have much higher errors. So this implies that there is some kind of non-equilibrium processes at work. And basically how these kind of processes on that scale are usually modeled is through reaction networks. So such a network looks a bit like the figure on the right. So generally a discriminatory network can be partitioned into two parts. So one part takes in a right substrate, which I denote by the letter R, does some stuff with it, maybe goes through some conformational changes, and in the end makes then the corresponding correct product. On the other hand, it can also take up some wrong product because maybe the substrate has some kind of some shape or some binding affinity that looks very similar to the right substrate. So that part of the network does the same thing as the right part, and it goes through some conformational changes, and in the end it makes the wrong product. So basically the way I drew it here is to illustrate the fact that these don't need to be symmetric. In practice they usually are. So if we, for instance, consider a protein or a ribosome, let's say, that reads some kind of template strand, it will not differentiate between whether or not it has bound a right or a wrong substrate in following the different steps in the network. So the network topology generally stays the same for right and wrong, but in what I will do next, we assume that they can be asymmetrical, and also that they can have a different number of states and a different number of catalysis rates. And basically, when we assume that all the reactions are reversible, then of course the thermodynamic uncertainty relation holds, which limits the precision of some current in the system by the amount of dissipated free energy or entropy production, which is the right side of the inequality. But generally, when biological experiments are performed, often these experiments do not give a result for the inverse catalysis rate. So basically, they model the catalysis transitions that form the products as irreversible and unidirectional. And if that is the case, then the original formulation of the thermodynamic uncertainty relation is not valid anymore. This would then lead to an infinite entropy production, and it needs to be changed a little bit. Luckily, this was done a couple of years ago, and the only thing that changes in the formulation is basically that on the right-hand side, the entropy production sigma now becomes the entropy production of the reversible part of the network, so the circled parts in the diagram, complemented by the average flux of all unidirectional transitions taken together. So generally for these kind of networks, we can define some observables. The most important of which is, of course, the error rate. We want to know how well does our system perform, how well does it discriminate right from wrong. And basically the way we can define this for any kind of topology is just taking the average flux of all the production steps that lead to the wrong product divided by the total production steps, so both right and wrong. Then we have the speed at which the process happens, and that is basically just the denominator of the error rate, but I've split it here into two parts for clarity, and it's just the sum of all catalysis fluxes in the system. So this is a unidirectional flux. And then to account for the precision of our flux observables, we define a quantity that's called the Fano factor, which is basically a noise to signal ratio. So it's the variance of a flux divided by the flux itself. And in what follows, I will just assume that I will calculate this Fano factor for only the production transitions. But basically we can take it for any edge in the network that we want. But here I will focus on production. And lastly, I will scale the entropy by the unidirectional current, or the speed in that sense, to have some notion of a reversible entropy production per product formed in the network. So with these observables, we can actually rewrite now this generalized TOR and get the equation on top for the correct product transitions. So basically the Fano factor of all the correct transitions in the network is bounded from below by the error rate and this reversible entropy production per product. And I can formulate similarly a bound on the wrong product formation and on the total product formation. So that is this FR plus W. And of course, this one does not depend on the error anymore because we do not measure it. If we just look at the number of products that is formed indiscriminately, then it's just bounded from below by the entropy production. Additionally, we have a kinetic bound in the limit of where the affinity of the production cycles go to infinity, and that is bound from below by 1 over m, where m is now the number of states in a single production cycle. And to illustrate how tight our bound is that we found, I will talk about two different examples. The first of which is a multi-stage Michaelis-Menten system. So this is the most basic discriminatory network. So an enzyme in a free state binds either a correct or a wrong substrate and goes through a series of conformational changes, with all of which are reversibly connected through reversible kinetic rates. And at some point, a product is formed with a catalysis rate F. And generally, we assume that these catalysis rates F are the same for right and wrong substrates, but that is not necessary actually for the bound to hold, so they can be different. So I will study how tight the bound is with respect to the right side of this inequality, which we define to be some kind of parameter zeta, which is between 0 and 1. So for a three-stage Michaelis-Menten network, we see actually that our bound, which is in blue, is relatively tight, but that it is intercepted from below by the dashed line, which is our kinetic 1 over m bound. And since we have a three-stage Michaelis-Menten network, this means that we have 4 states in one production cycle, so it is bound from below by 1 over 4. And it is relatively close to the true bound, which is given in red, and which we determined through a Pareto optimal front, which we found numerically through a genetic algorithm. So we see actually that this bound is very tight for high values of zeta, and then becomes less tight again for low values of zeta until it is intercepted by this kinetic 1 over m bound, after which, of course, it becomes tight again. So if we compare different stages in the Michaelis-Menten network, we can see that this bound holds for all stages, either it's 1, 2, or 3, and that it's relatively tight for all of them. So it has the same kind of dynamics. Now, the second network I want to talk about briefly is now a correlated version of the previous one. So now, instead of returning to a free enzymatic state when the system has produced some product, whether it's right or wrong, it now goes back to a free enzymatic state that depends on whether or not the previous product was right or wrong. So imagine that we start off in the free enzymatic state E sub R, and we bind some wrong substrate, and we catalyze it into a product. Then now, because the product we formed was wrong, we now go to a free enzymatic state E sub W, and we can start the cycle over again. So if we now look at the bound for that network, we see again that it's very tight. It's even tighter than the previous models. But an interesting phenomenon emerges here, that if we look at the Fano, the Pareto bound, so the red line, we see actually that there is a phase transition happening. So in the optimal protocol, which switches between a single stage Michaelis-Menten network and a 3-stage Michaelis-Menten-like network, so not exactly. And it's simple to see why it starts off in a single stage Michaelis-Menten network, because that just basically means that it is following this branch of the network. This is a two-state cycle in the system, so it is bound from below by 1/5. So if we were to analytically continue this line, it would go to 1/2. But at some combination of the kinetic rates, it switches to a different regime and now tends to follow the inner cycle, going through consecutive catalysis of both right and wrong products. And the bound even becomes more tight in this case. So we see that it switches to something that looks a bit like a 3-stage Michaelis-Menten system, but it's even closer to the TOR bound. So in that sense, it's even more optimal. So with that, I want to conclude my talk. So the TOR, it gives some universal bound for irreversible reaction schemes. In terms of experimentally accessible observables. The error rate is accessible, the Fano factor is accessible, and if we were to switch the Fano factor and the entropy production, this would give us a lower bound actually also on the entropy production of the reversible part of the network, all of which can be experimentally determined. And I determined that the bound is generally tight. And as an outlook, we are currently investigating or doing a deeper study of the Pareto front phase transition we found in this model. You can find all of our results in a recently published paper in Europhysics Letters of myself and my supervisor, Karel Proesmans. And with that, thank you.